for the invitation and the introduction. And thank you all for coming at this slightly strange time and working with my schedule. So today I want to talk to you about some of those data science tools we're using to explore climate projections, climate change, or more broadly, anthropogenic change. And you'll see why I use that slightly broader word here in this title. This is work being done by myself, but also with many collaborators. And so I just want to point out that this is really a joint effort across many, many brains, having a lot of fun with these tools for earth science. So let's talk for a minute about machine learning and specifics. So we're going to change a lot from the last few talks you've seen. So talk about machine learning, but machine learning for climate science. So in many ways, it might feel like machine learning has only recently appeared in climate or earth science research, but in fact has been around in atmospheric science specifically since the 1960s. Here I have a lot of pretty pictures showing you how machine learning is being applied today in our field. And I'll go through some of them. These are some of my favorite applications. So one great one is thinking about how we can use machine learning to do climate reconstruction. That's shown here at the top. So reconstruct, say, a temperature map from the 1800s with limited data. Another exciting one is equation discovery. Sometimes we think machine learning tools are sort of the opposite of physics or equations. And in fact, Zana and Bolton show in their 2020 paper how they use machine learning and data-driven methods to discover the tensors within their fluid dynamics equations. Another example is machine learning is being used for climate change communication. So here's an example on the bottom here showing, say, somebody's neighborhood and then using a specific type of machine learning to remake that picture under what might look like flooded conditions so people can visualize what climate change may look like or do to their neighborhood in the future. And then maybe more standard applications, but still just as exciting in atmospheric science and climate science is pure weather prediction. So in the upper right-hand corner, this is an example from Vane et al. Showing the true, the verification field of the geopotential height. And on the right-hand side, what their forecast was from a purely, this is 100% machine learning model. So no dynamical equations are inside. And their argument is it does, okay. We're not trying to sell it as, this is what we should be doing, but the point is maybe there's something interesting and exciting here. And then finally, the use of machine learning for convective parameterizations. And this is, to me, where a lot of exciting science is being done. That is, how can we use machine learning to make, for example, the simulation of clouds in our climate models better? So I list all of these because A, I think they're really exciting, but B, I'm going to take a slightly different tack here and talk specifically throughout my talk about explainable machine learning and how we're using it for science. And so I just want to point out that these are great examples, but I'm going to do something slightly different. Okay, so why might we use machine learning for science or science broadly, or maybe geoscience or earth science? Well, to me, there's really three reasons. One, it might be to do it better. So for example, convective parameterizations in climate models are not perfect, and maybe we can use machine learning to make them more accurate. Number two is to do it faster or cheaper. So another example is radiation code in climate models is very slow, but it's very good. And there are people using machine learning to try and help speed up this part of the code rather than, say, make it better. And then finally, and this is the bullet that I think sometimes people don't think about, is that we can use machine learning to learn something new. That is, we can go looking for nonlinear relationships in our data that we didn't know were there. And this is very relevant to research. So it may be slower and worse, but we might still be able to learn something as scientists about our system. And I'll touch on this in my second example today. All right, so example one, we're going to be talking about how do we, using machine learning to do it faster or cheaper. So here's the driving question for the talk today. The broad overarching question is that, humans are changing the Earth in profound ways. How does this differ around the planet, and how has it changed over time? So the first example today, I'm going to be talking about human pressures on the land surface and how we use machine learning to explore that question, that topic. And then example two is going to be more about climate model projections of climate change and finding indicators of climate change. So example one is thinking about the human footprint on the land surface. So here's a map of what is often called the HFI, or the Human Footprint Index. In this case, we're plotting it from 0 to 1, where a 0 or a dark blue color means, pristine forest, and a 1 means, you can imagine, means a shopping mall with a bunch of cement. So a lot of human footprint in that region. Now, mapping the effects of human pressure on the land surface at a global scale is a significant undertaking, and there are groups out there doing this. For example, this map was made, just published in 2020 by Williams et al., using a large range of data types to go into making this estimate. For example, they used information on the built environments, the population density, croplands, roadways, railways, waterways. All of this information went in to creating this product. Now, this is a lot of work. And so current efforts to do this tend to lag the present day by about 5 years. So this is a map for 2000, and their most up-to-date map is for 2013. And right now it's 2021. So there's a delay here. So we know development can take place very quickly, over a matter of just a few years, not decades. And so it would be really useful to have up-to-date metrics of this human footprint index. So what we did is we said, well, let's see if we can learn this human footprint index from satellite imagery alone. That is, we took Landsat imagery from the year 2000. Here are some examples. And we fed it into our what's called a convolutional neural network. And we output a prediction from 0 to 1 of this human footprint index. So this is our machine learning-based human footprint index. There are a ton of details. I've given entire hour-long talks on just this one small bit. I'm not going to do that here, so I'm going to cut to the chase and say, in the end, it worked. And we were able to make this map, which is the machine learning estimate of the human footprint index for the year 2000 from Landsat imagery alone. And you'll sort of have to believe me that it did a pretty good job. The bottom left, again, is that original Williams HFI, but it's pretty hard to compare them here on your screen, I realize. Now, what was the point of this exercise? We already had a human footprint index. We already had a pretty map for the year 2000. Why use machine learning to do it? Well, the point is that we also have Landsat imagery from the year 2019. So we can now easily remake this map for about 20 years later using the exact same machine learning tool that we have already trained. And so we are able to create a map that looks like this. So this is the estimate by our model of the 2019 Human Footprint Index. And if I flip back and forth, you'll see certain regions really brighten, and that's showing increased human pressures on the land surface in that region. Thus, we can create a near present index. Now, that's fine, but are these predictions any good? And I could show you error maps, and I could convince you that our error is generally okay. But you might still wonder, how can we check that this black box, if you will, machine learning approach is giving us the right answers for the right reasons? So to do that, there are many they're called explainable AI tools. One in particular is called Layerwise Relevance Propagation that my group uses quite a bit to do our science. And here's how it works. Imagine you have a neural network or a machine learning box here, and you have a picture of a cat. You put the cat into your box, and out comes the probability that there's a cat in the image. And let's just say it's 0.8. So the neural network here thinks there's a cat. What this particular method does is it takes that value and pushes it back through the network to create a heat map of the most relevant regions for that prediction. So in this case, this heat map, if you see down here in red, says the neural network looked where there was a cat to determine there was a cat. Not terribly surprising or exciting, but at least it's working, okay? So how is this useful, though, for doing science or for answering our question about the right answer for the right reason? So we're going to go through an exercise here. So a neural network was trained to predict if there's a horse in each of these images. And it turns out the network was very good at this task. So I want everybody to look at these two pictures, and hopefully you agree with me that there are horses in each of these images. And again, the neural network agreed. What we can use now is this method, this layer-wise relevance propagation method, to ask which regions of these pictures were most important or most relevant for the neural network's correct prediction. And these are the heat maps that result. Now, they're a total mess, but all I want you to do is sort of squint, and hopefully you can convince yourself that the red blobs generally line up with where there are horses. So far, so good. The neural network's looking where there are horses to predict there are horses. Let's do it again. 3 more images, 3 more pictures of horses. We agree there are horses in these images. The neural network got them right, but where did the network look to know that there was a horse? Again, we can use this method, and we find that the most relevant regions are not where there are horses, but are actually the bottom left-hand corner. You may have noticed that the bottom left-hand corner holds a copyright symbol and a copyright statement. So it turns out this particular network was trained on many images scraped from the web that all came from the same horse website, and so all had the same copyright image. And so this is an example of a neural network that's getting the right answers for the wrong reasons. And we wouldn't have known that if we hadn't been able to use one of these explainable AI strategies. Okay, so I'm not here to talk to you about horses. Obviously, I'm a climate scientist. So what does this have to do with climate and earth science? Well, let's go back to our changes in this human footprint index and how humans are impacting the landscape. We can look at changes in this machine learning human footprint index between 2000 and 2019. And what's shown here is the original Landsat image from 2000. The middle panel is that from 2019. And now the right-hand panel shows this heat map of the most relevant regions for the network's prediction. And what we see in looking at this is the network is indeed focusing on what we expect it to. That is, as humans go in and build wind farms in Texas, the neural network is identifying those wind farms and those new roads going in as the most relevant and important regions for its new prediction. So this gives us confidence then that the network's learning the right answers for the right reasons. Okay, so let's go on to example number 2, where we can actually use machine learning to do new science. So let's think about indicator patterns of force change across the Earth system. So if you think about detection of force change or climate change, there's a lot going on. So here are 2 maps of temperature trends over 2 different time periods of observations. On the left is the time period of 1920 to 1959, and on the right is 1960 to 1999. And overall, we see this general warming of the globe at these different regions. When we talk about, detecting climate change, we might ask questions about the patterns of this change. What are the patterns and which geophysical variables are most relevant or important for this change? You often think of temperature, but there are certainly other variables that people care about. How about the timing of this detection? When can we detect patterns of force change? And finally, model evaluation. Do climate models simulate these changes correctly, and how do they differ between each other? So I'm going to talk now about how we use machine learning and explainable AI techniques to think about some of these questions. All right, so here's the setup, and it's a bit strange if you haven't seen this work before. So what we're going to do is we are going to train a neural network to predict the year of a map. That is, here's an example, precipitation map in winter, or DJF, from a particular CMIP6 climate model. So we're going to input a map into this network, and we want it to tell us which year this map is from. Now, this is a pretty strange idea, but if you sit and think about it for a while, you can probably convince yourself that there might be something useful here. And in fact, what we've been doing with this approach is finding that the neural network must learn regional signals that are reliable indicators of the year. That is, it needs to learn the forced changes as a function of different year or decade or anthropogenic forcing in order to make the prediction correctly. Now, we have a few papers on showing how this method works, and it works quite well. But what's new here is asking the questions of what if you don't just input precipitation, but what if we use multiple variables at the same time? That is, we use combined variables to try and predict the year. That is, can we combine variables and seasonal information to better identify global change? So in this case, Jamin Rader, a master's student in my group, he's been inputting both surface air temperature and precipitation maps and tasking the network with predicting the year. All right, so how does it do? So this is the kind of plot we make a lot. So on the x-axis is the true year of the map that went into the model, the neural network, sorry. And the y-axis is the predicted year. So that dashed line is the one-to-one line, and that's a perfect prediction. Now, the little colored dots you see are for the testing data, so different climate models that the neural network has never seen. And let's maybe focus on the red plot, so temperature. if you notice, it starts off quite flat. So the neural network does a terrible job at predicting the year of a map until about the 1970s or 80s. And then suddenly it does quite a good job with its predictions lying along the one-to-one line. What this tells us is that the neural network is searching for these patterns, these indicators of change that tell us what year it is. That is, if it's hotter, it's probably a later year. However, it can't really find those patterns until the 1970s or so. The second thing to note is that the white dots are the observations. That is, after we've trained this machine learning model on climate models, we input maps from observations and we ask, what year is it? What year do you think it is? And the cool thing is we truly know what year it is in observations, obviously. And so we can assess whether our neural network has learned anything useful for the real world and the real world prediction. And again, these white dots tend to fall along the one-to-one line after about the 1980s or so. Now, the difference between the red, the blue, and the yellow is what variables we are interested in and what variables we feed the neural network. So in this case, what we find is that when we combine temperature and precipitation maps together, that is, we give the neural network more information about the climate system, it does a better job at identifying change, both earlier and more accurately. And indeed, it turns out that if you do this many, many times with many, many different neural networks, that in almost every case, the combination of precipitation and temperature information, it has an earlier time of emergence of the signal. That is, the detection of these patterns happens faster. Again, this is not surprising, but it's showing how neural networks and machine learning can help us make that, or can help us find those indicators earlier. Okay, so if you're sitting here going, wow, we just predicted the year, something we know quite well, right? My 6-year-old certainly knows what year it is. So why do I need a neural network to do this? So predicting the year, yeah, is pretty silly. I agree. But what if we could learn which regions of the globe were most important or relevant for predicting the year? That is, what if we could actually get those patterns that the neural network is using? And that, I think, is where the interesting science comes out. So if you remember, I already introduced Layerwise relevance propagation, or this explainable AI method. Well, we can use it in the same way we use it for the cat or the horses, or we use it to identify, wind farms in Texas. So what Jamin has done is he's used LRP to propagate the prediction of the year back through the network to ask which regions of the input maps were most relevant to get the year correctly. So here's an example of that relevance heat map. So this is a plot for JJA, so June through August precipitation. And the regions you see that are darkest are the regions of precipitation that provides unique information from the temperature indicators. That is, these are regions where the precipitation pattern is showing change that is unique and additional to what the information we get from temperature alone. Now, if you didn't use neural networks, you might think to make a signal to noise map instead. And that's what's shown here when it shows up. And the important point, oh, here we go. The important point with the signal to noise map is while there's certainly a lot of information on it, it is different than what the neural network has highlighted. And that's because the neural network is highlighting the most relevant regions as a whole, where the signal to noise map is computing each pixel by pixel separately. So that is, the neural network is truly identifying global patterns that are relevant and important. All right, so that's how we're looking for those patterns of change. An additional way we have been using this tool is to investigate single forcings in models. That is, trying to understand the interplay between aerosols and greenhouse gases in forcing change in our climate system. So this is work done by my postdoc, Dr. Zach Lade. And what he makes use of is a set of climate model simulations where they rerun the climate model with all of the same anthropogenic emissions, greenhouse gases, chemistry, etc., but they withhold one thing that they keep constant at, I believe, 1800 levels, so pre-industrial levels. He then does the exact same process with the machine learning approach and predicts the year. So here are the results. You've already seen plots like this where the actual year is on the x-axis and the predicted year is on the y-axis. On the left-hand side is the simulations that were run with all but greenhouse gases. So it has, volcanic eruptions, anthropogenic aerosols, biomass burning, but no greenhouse gases. In the middle is this climate model simulations with everything but anthropogenic aerosols, and on the right is with everything included, which is the standard in our CMIP and our climate model simulations. So the thing that turned out to be most interesting is the red dots are the observations. And you can see if you don't include greenhouse gases in the simulations, the neural network does a terrible job on observations. And that's because the observations look nothing like the climate model, right? The real world has greenhouse gases. So the neural network does terribly. But what's interesting is that it turns out the neural network does best when it is on observations, when it is trained on climate model simulations that do not have aerosols. And this is strange because we know anthropogenic aerosols exist in our system, right? We are outputting anthropogenic aerosols, and yet the neural network does the best on observations when those are withheld. Put another way, if you look at the correlation or how well the neural network does on observations, the highest values are always from the neural networks trained with climate model simulations where aerosols are withheld. Now we can use Layerwise relevance propagation again to go and explore why the neural network is doing a better job with the all but aerosols. And in this case, I'm not going to show a map, but I'm going to actually show the average relevance over Southeast Asia and the North Atlantic. And in the end, what we find is that the all but aerosols runs do the best on observations because they're focused on the North Atlantic, which is really believed to be a greenhouse gas signal, which is something that our climate models appear to be getting more correct than the response to and the input of anthropogenic aerosols. Okay, so wrapping up here, future directions. These were some very specific examples of how we're using explainable AI to detect change in climate models and the real world. But I want to point out 3 other exciting avenues, I think, in the work that we are excited about here. The first is the concept of knowledge-guided machine learning. That is, how can we make physics and machine learning work together? It seems a little silly that we're going to throw out hundreds of years of physics to just throw all of our data into a big black box, if you will. And so people are working on how to bring these 2 approaches together. Another is just generally, how can we use machine learning for the building, evaluation, and use of climate model projections? I've shown a few examples here in this talk, but I think this is just the beginning of so many exciting things we can do in this realm. And then finally, the concept of transfer learning. That is, how can we leverage our imperfect climate model output to actually make better predictions of observations? And there's a methodology for how we can train machine learning algorithms on climate model output and then try and update it with the small amount of observations we have to make better predictions of the real world. And this is, again, another way that I think machine learning can really help merge the world of climate models and the world of observations together. So my closing thought here is that explainable machine learning can open new doors for climate science and geoscience in general if we wield it carefully and intelligently. More often than not, scientists want more than just a prediction. We want to know why. At least that's why I'm a scientist. I want to know why. And explainable and interpretable machine learning really allows me to start to do that. And I think this is a game changer for scientific research. Thank you.